Nuclear forces. Inside the nucleus, we have protons and neutrons. You know very well, neutrons are chargeless, protons are positively charged. When you say positively charged, the protons might repel within the nucleus. That might break the nucleus. Nucleus will become unstable, atom becomes unstable. But actually, it is not happening like that. So, some other attractive force is there inside the nucleus. Between two neutrons, between two protons, between a proton and neutron, you have a nuclear force. It is not electrostatic force. Electrostatic force is very small compared with nuclear force. Sir, this has got some mass. I want to compare with gravitation force. Gravitation force is nearly 10 power 40 times less than that of nuclear force. So weakest force is gravitation force. So when you compare nuclear force with the gravitational force, nuclear force is 10 power 40 times greater. Gravitational force is 10 power 40 times lesser. Either way you can say. Yukawa, the scientist who observed this concept, he introduced mesons, intermediate particle, which is responsible for this strong nuclear force. So just introduction about nuclear force. Okay, next. Radioactivity. Madame Curie and Marie Curie, Henry Becquerel is a scientist who observed initially some basic concepts about radioactive nature. Henry Becquerel, he took a radium covered in the black paper, kept in photographic plate, kept it inside the dark room. After 2 to 3 weeks, he took the plate and developed. He could see some radiations in the photographic plate, some scintillation, some observation. Entire room is covered in dark room, so no other external radiation can come. So he observed that some kind of radiation coming out from that radioactive material, radium. Madame Curie and Marie Curie expanded that one. They observed that some charged particles present inside, which is naturally radioactive. It's not artificial, naturally it is radioactive. Meaning, lead chamber, radium. Why lead chamber? Lead is a thick wall. It will absorb the nuclear radiation. So we are using lead chamber. Radium is radioactive material. It is giving out some radiations. What are the type of radiation coming out? They want to observe. It provides electric field plus and minus. Here we have a photographic plate or fluorescent screen. They observe some of the rays are deflected towards positive, some are deflected towards negative, some are undeviated. The rays which are deflected towards a positive side should be negatively charged. The rays deflected towards negative side should be positively charged. And the rays undeviated has got no charged particle. That one they named as gamma rays. The rays deflected towards positive side, we call it as alpha particle. Positively charged. Beta particle, negatively charged. Gamma rays, it is not a particle, it is a ray. How they observed alpha particles, sir? Suppose you take X is a day. This is the element. Alpha particles being emitted. Then we observe atomic number of this reduces by 2. Mass number of the resultant reduces by 4. 2He4. Atomic number 2, mass number 4, means that is nothing but helium nucleus. So alpha particle is nothing but helium nucleus. This is parent nucleus, this is daughter nuclei. When you take the radioactive element is emitting a beta particle. Beta means we have beta plus and beta minus. Here beta minus we are taking. You can see atomic number increases by 1. Mass number remains the same. That Z minus 2 plus 2 Z, balancing the equation. Z plus 1 minus 1. Reactant side and product side, we should balance the equation. Why we are talking about the electron here? Electrons are outside the nucleus. How come we can talk about the electron here? Actually, here when we observe the number of neutrons, atomic number increases by 1, you said. What happened to neutron number? What is number of neutrons? A minus Z. But here what you are having? A minus Z plus 1. So A minus Z minus 1. One neutron number is reduced. That neutron only decays into a proton and electron plus an elementary particle called a neutrino. James Chadwick introduced neutron discovery in 1931. So this neutron number only changed into a proton Z plus 1, this electron and some elementary particle. When gamma ray is emitted, no change in atomic number, no change in mass number. Then you can ask one question, how do you know gamma ray is emitted? You find out the parent nucleus energy. After emission of gamma, so-called gamma ray, daughter nuclear energy. There is energy difference. So gamma ray is emitted, no atomic number, mass number change. You can observe. So this is basic information regarding the radioactivity. Rutherford-Soddy law, this is called. Rutherford law of radioactivity. We are not going to derive the equation, we are going to write the final step. Law of radioactivity, N is equal to N naught e power minus lambda t. N is called the number of atoms remaining unchanged after a time of decay t. N naught is the initial number of atoms present. Alpha, beta, gamma radiations are coming out, sir, from radioactive material. After 3 alpha particle decay, 4 beta particle decay, 10 gamma decay, we don't know. Depends. Final atomic number and mass number you calculate, so you know how many alpha emitted, how many beta emitted, how many gamma emitted. Find out the number of atoms present at that particular instant. At the time of starting the experiment, number of atoms present in naught. We are relating these two. Lambda is called decay constant or disintegration constant. This lambda depends on type of radioactive nucleus, what it is. Radium, thorium, uranium, radon, all these radioactive particles. Lambda will differ for all these things. Only the final equation here we are writing. We are not deriving the equation. Half-life period. Time taken for half of the number of atoms to disintegrate. T half. What is the meaning, sir? At the time of starting the experiment, I have 100 atoms. The time taken for that particular atom to disintegrate to 50. N is equal to N naught e power minus lambda t. This is the original equation of law of radioactivity. When time of decay becomes half-life, T is equal to T half. Then number of atoms remaining becomes half of its original value. Original value is what? N naught. Half of the original value means N naught by 2. Substitute N naught by 2 is equal to N naught e power minus lambda capital T. Half-life period. N naught cancels. Half is equal to e power minus lambda t. E power lambda t is equal to 2. Take logarithm both the sides. Log e to the base e 1. So lambda t is equal to log 2 to the base e. This is natural logarithm. You can convert it to logarithm to the base 10. Why we have to convert, sir? Logarithm, okay, if you want to find out the value to the base 10 only, you can calculate it. So multiply by 2.303 log 2 to the base 10. 2.303 log 2, 0. See the logarithm book and calculate for 2. 2 means 20.3010. Calculate T 0.6931 by lambda. This is T half. Half-life period. Every element, the lambda value changes, so half-life period also changes. Radon, half-life period is 3.8 days. Radium, half-life period is 10 power 9 years. So the value will change. Depending upon lambda, T half value will change. Okay. Next. Mean life period. Tau. Only the final formula we are writing. Total life of all atoms divided by total number of atoms. Sir, you are taking uranium 92, you to 35. It's going on emitting alpha, beta, gamma rays. It comes to lead, Pb 82, 206. That's all stable state. Lead is stable. Below this category, alpha, beta, gamma radiation will not come out. Elements whose mass number greater than 200 only natural radioactive material. So lead is a stable state. After that, alpha, beta cannot come out from lead. So how many atoms emitted divided by total life of all atoms? You calculate, find out, that is called mean life, and you can prove mean life period is equal to 1 by lambda. Lambda, you know, it is called decay constant or disintegration constant. Here also it is depending on lambda, here also it is depending on lambda. So definitely half-life and mean life, you can find out the relation. How? T half. is equal to 0.6931 into 1 by lambda. What is 1 by lambda? Tau. So half-life period is 0.6931 times of mean life period. This is only lesser. Only approximately 0.7 times mean life is half-life. Tau I want to calculate with T half by 0.6931. Mean life period is more. Half-life period is less than mean life. So this is the basic information in radioactivity concept. Okay, next. Nuclear fission. Only the definition we are going to see here. Nuclear fission. Nuclear fusion. Process of splitting up of heavy nucleus into two nearly equal fragments. We call it as fission. 92U235. When slow neutron is bombarded, see, slow neutron itself is enough to break the uranium. Binding energy graph we have discussed. Binding energy per nucleon for elements whose mass number greater than 200 is less. So, slow neutron itself can break uranium. Barium, krypton, 3 fast neutron plus some energy is liberated. We are not interested about the fission fragments. We are interested only about this fast neutron and energy. This fast neutron is slowed down. Combine with uranium. Again you will get. So, uranium, 1 neutron is hitting 2 fission fragments, 3 fast neutron, N1, N2, N3. You are slowing down. Moderator is a device which slows down the speed of the neutron. Heavy water and graphite. Again, initially 1, after that 3, then each 3, 9, 27, 81, it goes. This is called geometric progression. When you allow this to continue like this, you are getting uncontrolled chain reaction that leads to atom bomb. We don't want 3 neutrons, 2 neutrons you absorb. Only 1 neutron I want, sir. That will produce 3, absorb 2, only 1. So every fission reaction, you are absorbing 2 neutrons, only 1 neutron is coming out. That is called controlled chain reaction. That leads to nuclear reactor. Uncontrolled chain reaction leads to atom bomb. Okay. Nuclear fusion. Process of combining 2 or more lighter nuclei to form a heavier nucleus. Process of combining 2 or more lighter nuclei to form a heavier nucleus. You call it as nuclear fusion. Already we have discussed in binding energy. Lighter nuclei possess more binding energy. It is not a chemical reaction, man. You cannot take 2 things in a test tube and then add. No. Nuclear reaction. Enormous amount of energy required to combine. So, to combine these lighter nuclei itself, we have to provide some energy. Sir, why we have to waste? Initially, nuclear fusion, if you want to start, nuclear fission energy you are taking and then you are initiating. Enormous amount of energy is coming. The fusion reaction taking place inside the sun, inside the stars. Sun has got enormous amount of energy because of fusion of gases. So first it has got a trigger and got the energy, and continuously the gas is going on happening, fusion is happening, you are getting enormous amount. Plasma temperature is 10 power 7 Kelvin photosphere. 14 million Kelvin. That is 1.4 into 10 power 7 million Kelvin. 0.4 into 10 power 7 Kelvin. Central core of the sun. Right? So proton-proton cycle is taking place inside the sun. Carbon nitrogen is taking place inside the stars. We have some stars whose temperature is more than that of sun. Then why we are not getting that one, sir? It is so far off. Nearest star of the earth is sun. So this is basic introduction about nuclear fission and the nuclear fusion. Thank you. We continue.